Hello everybody, my name is Stas Burov, and this is a class of Statistical Physics. Statistical Physics. My name is Dr. Stas Burov, and please just use my first name, which is Stas, to ask questions or anything else. Now, before we are actually going into diving into the statistical physics, I would like to describe what I'm going to teach, and even before that is what are the technicalities of the class. That's mainly what is the composition of the grade. What are your obligations for the class? And we will have quizzes and we will have homework, and how everything is graded. Okay, so basically, each week you will get home assignments. Home assignments will be uploaded to the website of the class. I hope you're familiar with the Moodle system. No? Yes? Well, Yossi will describe it. So, lemida.moodle. You don't have an access? Okay. So don't worry. This week there are still no home assignments. So yeah, by next week I hopefully you will get passwords and access. But so everything will be there in terms of my announcements and home assignments. COIL, I think. Okay, but this is from next week. What else? Basically, so each week you'll get home assignments. There are approximately 13 homework assignments for the semester. You're obliged to submit at least 11 out of this 13. The grading for homework is 11% of the final grade. Okay, so this is the home assignments. They are not going to be completely checked. At least only some of the questions are going to be checked, but still the grade is 11%. What else? Quizzes. There are going to be 3 quizzes per semester. You're obliged to, you can get all 3 of them, but the grading is going to be based on the 2 best grades of the 3 quizzes. So there are 3 quizzes, and the final mark is 22% of the final mark. And 67% of the total grade is the final exam. Okay. Nobody is going to force you to submit the homework or do the quizzes or do the final exam, but in order to pass, in order to get good grades, you actually need to participate in all the assignments given here. Any questions about that? No. Great. So my room is where I'm located. Is room 314 in this building. 202. I don't have office hours in a sense that my office is always open when I'm there. So you can come with questions whenever you like. Please don't come on Sunday. Sunday are my busy days. Anytime else, the office is open and you are most welcome. Anything else about the technicalities? Sorry, the mic is down. I think this is it. Oh, so The teaching assistant is Michael or Michael, and he's teaching you, I think my class is between 10 till 1 p.m. And immediately afterwards you have the same class with Michael. He's my teaching assistant, and he's going to provide specific questions for workout. What I'm suggesting, because we have 3 hours here, and 3 hours in a row it's too much, what I'm suggesting that we will do is that we will have 2 sessions from 1 till 11:10, 20 minutes break, and from 11:30 till 12:40 the second session. Any objections? No? Great. Okay, so this is the technical stuff for the class. Now we are going to discuss a little bit about, literature is also important. Literature. So there are many books about statistical physics, from classical one to very modern one. I will try to present in this class a little bit a modern approach to statistical physics, which mainly takes into account what happened in statistical physics in the late 60s and middle of the 70s with invention of a renormalization group and understanding how long-range correlations should be treated in real-life systems. And hopefully we will be there. But in general, I will use the books of Reif. They're all called either statistical physics or either statistical mechanics. Landau, Lifshitz, McGuire, and Chandler. Now, there is definitely no obligations in reading those books. All the material is going to be supplied here on the board. You can afterwards ask me or my teaching assistant. But if you want to read a little bit more, so some of the material, at least the basic, is going to appear here. More advanced material I'll probably will take directly from the research papers. Okay. So what is statistical physics? When I was an undergrad and I learned statistical physics, now the book, I don't remember its name, that the professor was using was started at this specific quote. It said, Boltzmann studied statistical physics and researched it, and he committed suicide. Afterwards, Ehrenfest studied statistical physics, and he also committed suicide. Now it's our turn to study statistical physics. Don't worry, it's not going to happen. But it's an interesting fact that several people, and there is a whole website concerned with conspiracy theory about the connection between statistical physics and suicides of this groundfathers of the subject. But the only thing that it's interesting about this is that statistical physics is a very interesting subject, sometimes very frustrating. Maybe because of that, all of this happened, and it was very controversial at the beginning of the era of statistical physics, which basically started with Boltzmann in the 19th century. What is so interesting about statistical physics? So think about classical physics. I'm not going to describe what happens in quantum mechanics, but think about classical physics. Classical physics and Newton description of the world. Okay. So we have Newton description, which basically says that everything is deterministic, right? We have m x dot equals f of x. Give me the force. I will provide you the acceleration. From the acceleration, I can study what are the velocities and what are the positions. So if everything or all the forces and initial conditions are known, I can completely solve everything. Okay? Everything is very, very deterministic. What is the problem with this description? It becomes very complex when the number of the particles, the number of the ingredients becomes large. Okay. So if I'm thinking what is the amount, okay, of particles, air particles, okay, oxygen, hydrogen, etc., in this small amount of air. And the number is huge, enormous, okay? Think about that the Avogadro number of 1 mole is 6.022 multiplied by 10 to the 23. I think I'm not mistaken with this number. So this is the Avogadro number. And these are the numbers or the base units that we are measuring with any complex system or any macroscopic system when we are trying to say what are the numbers of the molecular constituents of the system. Now think about it. Can I actually write 10 to the power 23 equations? And more than that, there is a strong interactions between all these particles. So actually starting with Newton equations for macroscopic system and trying to describe what happens on the molecular level is simply impossible. Okay? It's, well, maybe if one day we'll have quantum computers and we actually know all the initial conditions, etc., maybe we can do this. Probably not. Okay? So starting with Newton description and ending describing macroscopic situations involving a lot of particles is simply impossible. Even when we have 3 particles, the 3-body problem, it's already impossible to solve analytically. Maybe now we can simulate this. But think about 100 years ago, it's just basic, the starting of chaos, etc., Lyapunov exponents. So this route of going from Newton description, deterministic description, and ending up describing macroscopic situations is a false one. I urge you to ask questions if anything is not clear. It's very custom here in Israel or anywhere else. So where statistical physics come into play here? Historically, 150 years ago, people were trying to understand what happens with gases and macroscopic substances, especially how to produce work and use them to produce work. This is how they started to understand that Newton doesn't work when I boil a chamber of gas or a chamber of water, okay, in order to produce heat, in order to run an engine, okay, but something else takes place. And what is this something else? This is were the first thermodynamical laws, which actually forgot about the Newton description, and they say, well, there are specific laws, thermodynamical laws, statistical laws, that describe the system on a macroscopic level. I don't really know what happens to each molecule. And actually, I don't want to know. What I need to know, are there emerging behavior that comes only due to the presence of a lot of molecules and a general type of interactions. Right? So those are statistical laws because there are some sort of ignorance that I introduce, and this ignorance is saying, well, you don't know what happens to each molecule. You don't know what are the specific conditions, initial conditions for each molecule, and you don't really care. And even when you don't care, and even when you don't know what happens to each molecule, there are some very general and great things you can still answer, or you can still at least understand about the system only based on this simple statement. Statistical laws emerge when a lot of particles, when a lot of ingredients are taking place. When a lot of games are now playing in the same system at the same time. So ignorance, in some sense, it's a bliss. Because by treating fluctuations, by treating what seems random behavior, for me, why it's random, because I cannot describe it by Newton description, it looks to me very complex and stochastic. Maybe it can be described by Newton. We don't go there right now. But by taking those fluctuations, those statistical behaviors, I can devise general laws, and this is what we are going to try and perform in this class. And those general laws started to forget that we're treating hydrogen here, or we are treating radiative transport in astrophysical questions. And this becomes fantastically great, because the same physics and the same behavior happens on the scale of intracellular transport, for astrophysical radiative problems, or a flow of people into a stadium. Because in each situation, which is very, very different, this is a biological question, there's a lot of biology is involved, okay, or at least what we can think of it in this perspective. Here are intracellular structures, stars, black holes, etc., etc., general relativity. And here is human interactions where I'm coming with my body to watch, I don't know, a soccer game, and we're stuck in this big jam trying to get into the stadium. The behavior of the transport is described in a very similar fashion. Why? A lot of ingredients, some specific hardcore interactions, and voila, we have a general statistical law. We don't know what happens for a specific entity in the cell, or for a specific star or radiative imbalance here, or what happens to me specifically as a Stas on my way to the stadium. But in statistical fashion, what happens to me or here will be the same. The statistics is the same, the personal behavior is different. But in any case, I am not able to describe my personal behavior because of the general complexity. So our goal in this class is to understand, or to devise the initial and fundamental laws that can later on give us the answer of how statistically treat complex systems. Okay. Any questions so far? No. Great. So what we are going to describe now, before going into this great questions about intracellular transport, astrophysical physics, and human flow, actually we start with the classical questions of thermodynamics. I assume almost no prior knowledge of this subject. Now, why should I start from thermodynamics? Because of the basic understanding of macroscopic systems. Okay. So we start from thermodynamics. Specifically, we start from basic laws of thermodynamics, and the first law of thermodynamics. Now, I'm going to describe it to you, those laws. You're interested specifically in the first law and the second law of thermodynamics. I'm going to describe it to you in a somewhat mathematical fashion. Okay? But in the first place, those laws were devised from experiments. Boyle or whoever studied gases, studied the mechanical properties, and based on, tried to construct engines that works, for example, the Carnot engines that we heard of, or at least familiar with. And based on this study, on this interest of how I can actually manipulate nature, they devised specific laws. One of these laws is the law of thermodynamics. Now, the law of thermodynamics assumes something. It treats energy. Okay? And it treats energy or describes the energy of a system in a very specific way. So I mentioned here energy, and I mentioned system. Now, what do I mean by system? And generally we'll describe it to you as an artificial square, and we'll say, well, this is my system. What I mean? I mean that it has a lot of small ingredients, okay? Different molecules, different gases. It can be a rubber band. The only thing that I assume that it's a macroscopic system with a lot of ingredients inside. And they all somehow interact with each other. Okay? It can be 2D, 1D, 3D, okay, if I'm talking about a gas. Right. So for me, the system is a macroscopic object that I somehow prepared, right? And I assume that it has huge number of ingredients. We're talking about moles of ingredients, okay? Each mole is 10 to the 23 number of particles, and I can have a lot of them there. So this is the system. Energy. We learned a little bit about energy already in mechanics, and it's really, really hard to describe what energy is. I usually know of ways of how to change energy, but not exactly what energy is. I know that energy is something that is conserved in mechanical system, okay? And I know how to change energy by doing specific work. We will come to this in a second. But the laws of thermodynamics, or the first law of thermodynamics, assume that energy is an extensive, or at least internal energy, is an extensive quantity. What I mean by this? What I mean here is that my system is a macroscopic object. And I look on each quantity here inside my system. I have a lot of them. A subsystem. Okay? So this is a subsystem. In general, my system is constructed from a lot of subsystems. What I assume is that the energy of the big system is just the sum, or at least internal energy of the big system, is a sum of all the energies of the subsystems, as long as everything is macroscopic. So I'm still assuming, so even that the subsystems are macroscopic on their own. So E, energy of the whole system, is just a sum over I. I'm summing, going all over my subsystems of the energies of internal energies of the subsystems. Internal energies of the subsystems. The extensive part comes in the following fashion. When I'm already assuming this, the extensive part comes, extensivity, if I have two big macroscopic systems. This has an internal energy, E1, and this guy has an internal energy, E2. Each of them is a macroscopic object. Okay. Each of them is constructed from a lot of subsystems. Each subsystem is macroscopic object. Extensivity means that the total energy of 1 plus 2 is just the sum of the energy of system number 1 and the energy of system number 2. Right? This is what extensivity means. I increase the size of my system, the energy or internal energy increases. My system was 1 square. It had energy of some number 10. It's now 2 exactly the same squares, so the energy is 20.
Why it need to be macroscopic?
Okay, well, so let's assume that it's always hold. Now I'm trying to dig up. So I have here a chamber of a gas, right? And this chamber of the gas has 10 to the 23 number of particles. It's a mole of hydrogens. Great. Now I've subdivided into smaller systems. Eventually, I'll have a smaller systems, and each smaller subsystem has 1,000,000 particles. Okay, 1,000,000 particles is still a very big number, and the energy is still just this. Is the total energy is the sum of all of my smaller systems, subsystems. Now then I take my subsystem, okay, and I subdivide it again into millions of pieces. Okay, this is already somewhat artificial, because if there are strong correlations between the different particles, it won't work. But let's assume that it's an ideal gas. So the different molecules of the gas are not interacting with each other. Okay, so great. So I had 10 to the power 23 systems, and now after an additional subdivision, I have 10 to the power 23 particles, and now I have 10 to the power of 23 subsystems. So each particle is a system on its own. Okay? Particle is not a macroscopic object, it's a microscopic object. And you're asking me, why can I do that? So only in the case where they are not interacting, I'm allowed. Why I'm not allowed in general? Because think about it, can I subdivide even more? Can I now subdivide into a smaller system? So basically take each particle and describe it as 2 systems. Okay? I have here a classical description of a molecule. Okay? So here it's like neutrons, protons, and here I have electrons. Okay? It's a classical description, it's not true, but think about it as it is. I will try to subdivide it into 2 systems. I can't just describe this energy as the energy of the nucleus and the energy of the electron. It won't work. Okay? I can basically take them apart, right? And the total energy won't be conserved, because part of the energy is the energy that's responsible, okay, for keeping this electron near this nucleus.
But in macroscope systems also you have interactions.
Yes. Yes. So I'm assuming still here that the interactions between different systems are not very strong, and I'm talking about internal energy. Okay? If I'm having an external energy, so for example, energy that's coming from an external force, gravitational force, electrodynamical force, that's already not true. Here the whole discussion is about internal energy. And for the internal energy, I'm assuming that I'm not breaking stuff. You're right. I will come to systems where, so for example, the total energy comes from different dipoles. And in some approximation, it's just the sum of the dipoles. But there is additional part is coming that it's not linear, right? I'm sorry. So this assumption about extensivity holds true as long as it's not broken when the interactions are too strong. This is the whole point. I'm assuming that the internal energy of my system is such that it's extensive. When my system is becoming something different, okay, when the interactions are strong and long correlated, I maybe will have to treat it a little bit differently. Now coming back to the extensivity part, I assumed, or not assumed, I defined extensivity as a quantity that it's a dependence on the size of the system. And from this equation, I can tell you that extensivity means linear dependence on the system side. This is what I mean by extensivity. So when I'm looking on a system and I'm saying, or a quantity like energy, internal energy, and I'm saying internal energy is extensive quantity, what I mean is that that the energy is dependent in a linear fashion on the size of the system. Great, but so we know that our thermodynamical first law assumes something about energy, and it's conserves, or at least it says something about the macroscopic system, and its specific mathematical description is described basically as a conservation of energy. So if I have a system and the internal energy of the system was changed, the first law says that it can be changed only due to some mechanical work that have been done on the system or performed on the system, or a transfer of heat that was performed to the system or from the system. Okay? So this is change of internal energy. This guy is worked or mechanical work that was performed on the system. Okay, and the amount of heat that was brought to the system. Later we will see that the energy is something, and there is a change in the energy, and this is a specific, particular, a well-defined mathematical differential, as we know it. Here, I'm using a slightly different letter for the D. This is a D with some strike over it. This basically means that it's not a precise differential of the work. It's just the amount, the change of the work that what has been done. And the dq is the change of the heat that was performed to the system. Again, it's not a precise differential on its own. So the work, at least we intuitively understand what is mechanical work. I can pressurize the system and I can torque the system, at least, for example, if I have a rubber band, I just can try and tear it. Okay? The heat is also something that we intuitively understand. Okay? So for example, I have a chamber of water. Sorry. So I have a chamber of water, and I'm heating it on a stove. Great. And I'm just heating it from below. I know that after a while it will heat up. Okay, there would be some hot air coming from the top side, and I actually can use this hot air, okay, or this air in order to perform mechanical work. Okay, this is how first engines were devised. Now, the heat, I'm not doing any mechanical work on the system. I'm just heating it up. Okay. This is dq. The change of the internal energy that afterwards I can use in order to perform specific work that has been done not due to a mechanical application, but due to something else, and this something else I'll call heat. But intuitively, we understand this. I'm hitting up something. This is clear for all of us. But I'm not very well defining it mathematically right now. Mechanical work can be defined mathematically. Okay. Mechanical work can be defined mathematically. And we generally says that the change of the mechanical work is some abstract forces or mechanical forces multiplied by a change of an extensive variables. Now, it's not simply multiplied, but here I'm using dot, which is basically says that is vector multiplication. Okay. Scalar vector multiplication. Scalar vector multiplication. So what is F and what is X? So X is an abstract mechanical force. Mechanical force. Now, it's not exactly a force, as we will see it. It's something different, a little bit different. And X, it's a generalized force. Let's call it generalized force. And X is an extensive variable. Let's call it mechanical variable. Extensive mechanical variable. Why I'm using those strengths for the force? Because actually, from the definition of work, this is right? What is work, mechanical work? It's a scalar multiplication of force performed in a specific direction of moving the object. This is what we learned in the class on mechanics. Why I'm using here generalized force? Well, for example, we know that if we have an external pressure minus P external multiplied by the change of the volume, so this is external pressure, this is the change in the volume, This is so if I'm applying external pressure and my volume was changed by dV, I know that this guy is the change in the work. But P, which is a pressure, is not a force, right? Is a force divided by some area that I'm applying it to. Okay? The simplest example is I have a chamber of gas and I have a piston over here. Okay? And basically the pressure is the force divided by the size of the piston. Right? And I have some sort of a gas inside here. It's not a force. But if you look on this, okay, we see this is a force divided by area multiplied by volume, and eventually we get force multiplied by distance, because volume divided by area is just one-dimensional distance. So this is indeed a change in the, or indeed work. But since I'm writing it in somewhat different perspective, because my variable now is volume and not some specific distance, is the total volume of the system. Okay, I'm using P external as my generalized force. Okay. So the definition of force is not a regular force that I'm applying to the system over here, but it's a pressure. Why? Because I want to describe the whole system by using the variable volume and not using the variable, the position of the piston. Another example. I have a rubber band and it has a tension. The change in the energy, and it has a size L, the change in the energy is simply the tension, let's use another letter, F, multiplied by the L. Okay? Very simple here. Tension is some sort of a force. I change my size of my rubber band, and eventually I'm producing work by doing so. Right? So this is an additional example where work was performed by application of force. Here it's more clear to understand that F is my general force because it's just force multiplied by distance. But it's not only distances, even when we use other mechanical variables like volume, whatever comes in front of this differential, I'm using the term of a force for it. Now, why have written here as a scalar multiplication? Well, because generally I can have a lot of forces. Okay? I can have pressure, I can have tension, I can have whatever I want, no matter what my generalized forces are. So it's very easy, or easier at least, to write force as a vector of different forces, generalized forces, although they can actually be applied in the same direction. Okay? And what we say here is that force 1 multiplied by the change of external variable, not external, extensive variable x1 plus F2 by the change of extensive variable x2 plus F3 by the change of external variable 3. So it's not that we are taking our force and we're saying, well, it's a pressure and the pressure is three-dimensional. No, this is not what I mean. I just mean that I can have many generalized forces and there is a specific extensive variable that is associated with this kind of a force. Okay? So for pressure, the association is volume. For tension, the associated variable is the length, and etc., etc. This is great. So we understand work. There was an additional part. What was this additional part? Heat. Now, we understand what heat is, or at least what heating is, heating an object, but how I describe this mathematically. So I won't describe mathematically what is the change of the heat. I at least try to persuade you intuitively that we do know how to heat the process, but I still need a means for controlling my heat. And what I mean by controlling my heat, here I know that by a change of the position of the piston, I can perform work or stop performing work. Okay? By trying to pull this rubber band, I can perform some work on the system or stop performing work on the system. For the heat, I'm saying that I construct a constraint that can prevent a flow of the heat into the system or outside of the system. So this is my system, and I claim that I can construct a specific type of walls, okay, which generally I can adiabatic walls, that there is no flow of heat from the outside world to the system or from the system into the outside. Think of refrigerator. It's constructed in such a way that the big engine that sits, actually cools everything down, that sits on its backside is not transferring heat inside the refrigerator. Okay? Otherwise, all our food will, be very, very bad for you. Okay? So those type of walls are called adiabatic walls, or in general adiabatic constraint. Can also apply this adiabatic constraint and divide the system by some type of wall that, again, there is no flow of heat from one part of the system to another. So those are my means of control of heat transfer. Okay? So here I can apply or not apply generalized force. For the flow of the heat, I can apply or not apply adiabatic walls. And in general, I call a process adiabatic when there is no heat transfer during this process to the system or from the system. Okay? So adiabatic walls, or in general adiabatic constraints, are the means of how I can control the flow of the heat to the system or from the heat system. I haven't described you what is D of Q. I just said, well, there is a mean of control. I can apply adiabatic walls, and then D of Q is 0. When I'm not applying a adiabatic wall, dq is something. And what is this something? I haven't told you yet. Okay, great. So what we learned so far? We learned that we are treating macroscopic objects. We are assuming that the energy is extensive because it's a macroscopic object and it's just a sum of different other macroscopic objects. And of course, as your comment came by, sometimes it's wrong. Sometimes I cannot just say that it's the total internal energy is a sum of energies. I described the first thermodynamic law, which basically says that the energy is conserved. The change of the internal energy can be achieved or by heat transfer or perform some sort of a work. Now, when I know that I can have a system and I can apply work to it and can drive heat inside the system or outside of the system, I can also describe the system in some specific state. What I mean of a state? I mean that if this is my system, and I defined what are the values of my macroscopic generalized forces for the system. So generalized forces are defined. Extensive variables are defined. Okay. My constraints, adiabatic constraints for the systems are also defined. I know that this wall is adiabatic and this wall is maybe not adiabatic. Okay. By defining all of this, I'm saying I know what the state of the system is. Okay. So I'm not actually defining all the different positions of the macroscopic molecules that are here in the system. I don't care about them. There are too many of them. But I have a small number of parameters that I'm using to define the system. What are those parameters? My generalized forces, pressure, tension, my constraints about adiabatic processes. As usual, I will impose some adiabatic walls around the system. So existence of those walls or non-existence of those walls are something that describes my system. And I know that what are the sizes of my systems are, because extensive variables basically means something about the size of the system. It's always a linear dependence on the size. So I know what is the volume of my chamber of gas is. Now I have very small number of parameters over here. Okay, the constraints, forces, extensive variables, very, very small, especially when I compare everything to the total number of molecules that I have there. So by defining those small number of parameters, I'm saying that the state of the system is A. I'm changing one of those parameters, forces, constraints, extensive variables. I change the state of my system. Okay? So when I'm saying that my system in some specific state A, what I basically mean by this that I defined the generalized forces and extensive variables, and also the constraints. So this is a general definition of a state. What is an equilibrium state? Can somebody guess, maybe, what's an equilibrium state? So equilibrium state is when I define my generalized forces, I define all my extensive variables, I define my adiabatic constraints. Okay? So everything is defined over here. Everything is defined. And I leave my system on its own. When the system or the states of the system are not changing as a function of time, it's not growing, the volume is not growing, the temperature, we'll see what it is not changing, the amount of heat, there are no flows of heat, the generalized forces are not changing also, I claim that then my system in a state of equilibrium. So basically, equilibrium state is independence of time, stability. Okay? Then when everything becomes stationary, I defined my adiabatic constraints, there are no flow of energy or of heat from one part from the system to the outside world. I defined my extensive variables, the system is not growing or shrinking in its size. I defined in my forces, there are no change in the pressure inside the system. So not only from the system to the outside, but also there are no big internal flows. Okay? I cannot accept that the heat will be somehow transferred along again and again inside the system. This is not an equilibrium state. Equilibrium means independence of time. And it also means that I don't care how the system was made up. Okay? I heated the system or I cooled the system. Now this is the equilibrium state. It doesn't care how it was actually brought to the state. Okay? The only thing that I care that the state exists, and when the system in this specific state, it does not change as a function of time. Okay? This for me equilibrium, and it's going to be a very important concept. Okay? Because I would talk mainly about equilibrium states. And the thing is, when I'm talking already about equilibrium states, I forget how I actually came to this equilibrium state. The only thing that I will care about is, well, now I'm in equilibrium, and I'm completely ignoring the time processes. Now, what is an equilibrium? Equilibrium where I have a state, I have very small number of parameters, and those parameters are not changing, and they are sufficient in order to describe the state of the system. Okay? So in order to describe an equilibrium state, I need a very small number of parameters, and they are not changing as a function of time. For a non-equilibrium process, A, there is some dynamical process going on. B, the number or small number of parameters is not sufficient anymore. Okay? Because if I need to describe some specific flow, I need to describe what particles, for example, are taking part of this flow, or where this flow is actually occurring inside the system. So I need more parameters. Okay? At some point, is when everything is very, very non-equilibrium, I maybe need to know everything about everything. But in equilibrium, the claim is only small number of parameters is sufficient to describe the state of the system, and it's not going to change as a function of time, and I don't care how the system got into this equilibrium. Most of the systems that we are looking upon are in some equilibrium. The state of this board, or this board, is not changing as a function of time as long as I'm not drawing my silly pictures on top of it. Okay. It's stationary, it's static, as in some sort of equilibrium. When we look microscopically on it, we will see that there is some other processes that are actually happening inside. But the tension of this board, its size, generally not changing as a function of time, and we can assume that this is actually equilibrium. And most of the materials that we are looking upon are like this. Exceptions are glasses. Okay? Glasses, although they look to us that the size is not changing, and they are at the same temperature, the same size, the same pressure, this is not right. So in glasses, the glasses are exceptions. Glasses, the state is not an exactly equilibrium state. It's termed a glassy state because if you look on the windows and you will measure the top size and the down size, you will see a difference. And actually, a glassy state, and each glass, there is some kind of a flow, constant flow of the material. It's very, 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 very slow, but it's still there. Okay. Now that we have the first law, and we know what is equilibrium state, we know that there is energy and internal energy in the first law. What we are coming to is to description of the second law of thermodynamics. Any questions so far? No. So what is the second law of thermodynamics? And I will write it on the bigger board because I need more space. So usually the second term of second law of thermodynamics has something to say about flow of heat or temperatures and etc., etc. We will write it down in a slightly different fashion. Maybe more than one. The second law. And it says there exists a function of a state What is a state? I already told you. A small number of parameters, like generalized forces and extensive variables. We'll call that function S, E, and X. Okay. So there exists a function of a state such that its dependence on E is monotonic, i.e. it monotonically grows with E. Okay, so there is some function. I'm not telling you what this function is, but there is some general function that depends on the internal energy and the extensive variables. Those extensive variables define the state of the system, right? And this function, as I increase my energy, this function is increasing. As I decrease my energy, the function is decreasing. Okay. another concept. If the system can start from state A and reach in a adiabatic fashion, state B. Okay, so there is a transition from state A to state B that happens in an adiabatic fashion. Okay, so basically it means state B is reachable. I leave the system, not even I'm applying some forces. I'm leaving the system in some specific state A, and it spontaneously, or it's in an adiabatic fashion, reaches some state B. I know that SB is greater than SA. Okay. So this function S is growing as a function of energy, and it can reach, if it starts from state A and reaches states B, if it's performed in an adiabatic way, okay, this function is growing. The function is scalar. It basically gives me a number. Okay? Although it's a function of vectors, it eventually produces me a number, some specific number. Moreover, if one can reverse the process, so I can go from B to A. So the first part, if I'm going from A to B, okay, my S is growing. But it's also, if also this process is reversible, okay, I can also go from B to A, again in a adiabatic fashion. So I'm not losing heat on my way. Okay. So if I can start in state B and reach state A, then it means that SA is greater than SB, right? I started in state A, I reached state B. Okay? This second law says SB is greater than SA. But if I can also start from state B and reach state A, basically I'm reversing my process. SA is greater than SB by, again, this second law. And basically this means that SA equals SB for reversible, for states connected by reversible process. Reversible process. What it means, reversible process, is in the process my extensive variables are changing little infinitesimally. And reversible process means that each change is reversible. So for example, in this process my volume, it grew slightly. What I mean is that, well, I can now reverse it and shrink my system a little bit, okay? And then the system comes back exactly to the same state. Okay? So this is a reversible process. Now, it should happen very, very slowly, because at each state in the middle, I should assume that my system is in equilibrium. So when I change my extensive variables, at each stage of this change, the system is still in equilibrium. It's called a quasi-static process. Okay? Now, since I'm actually claiming that the system is reversible when at each stage of my process, each infinitesimal change of my variables is also reversible, so basically I'm claiming if I can start from state A and reach state B, on the way I will be in a lot of equilibrium states, And the changes from one equilibrium state to another equilibrium state happens very, very slowly, and it's reversible because the infinitesimal change of my extensive variables being very, very small. I'm sorry. If two states that are, again, equilibrium states are connected by such a process, okay, then this function S and function S is exactly the same for the two states. Okay. Now, I just remind you, this function is a function of state. Moreover, it's a function of an equilibrium state. So in order to define it, the system must be in equilibrium. S is defined for an equilibrium state. S is growing when I'm starting from one equilibrium state and I'm changing fastly into a second equilibrium change by some process. And if those two equilibrium states are connected by reversible process, okay? Reversible, I mean I can imagine some quasi-static process, very, very slow, that takes me from state A to state B, okay? Then the SAs and SBs are exactly the same. What is the name of this function S? It's entropy. Okay. So S is called entropy. Oh my God. S of X is entropy. And as we describe it right now, is defined for equilibrium states. And it's defined when I know everything about the state so far. Okay, we start again. So what we have reached at the last lecture, we reached that there is something which we call entropy. Entropy is a function of state. What I mean state is energy and X. And if I have two states that can be connected by reversible adiabatic process, reversible and adiabatic process, I can get from A to B or from B to A. And what I mean by this, increase the volume, decrease the volume, increase the pressure, increase the length, decrease the length. And if those two states are reversible, then the entropy of state A equals the entropy of state B. When the process is not reversible, then the entropy always grows. Right? Now, when I'm saying here or stating here that the S is a function of state E and X, what I actually mean is a function of an equilibrium state that's defined by E and X. Okay? It's important. Most processes in nature are not reversible. Okay? So usually, if I leave the system and I will let it grow, okay? So I had a ball, for example, and I heated it up, and now it stays in a I'm continuously heating it up. Okay, basically this ball can be in an equilibrium state. Now I take this ball and I'm actually throwing it into a very cool chamber with very cool water, okay? Swimming pool, for example. The temperature and this ball will start to lose is heat very, very, very fast. Okay? Can I then say something about this energy, entropy, or define the entropy over there? Well, no, actually, because now it's not in equilibrium. It's a different state, right? But it's not in equilibrium. And entropy is actually defined when the state is defined and the system is in some sort of equilibrium. if the process that happens right now, so in order to describe what happening to the ball, it's not enough actually to say, well, there is this big swinging pool around it, okay, and so the temperature is such and such. Because there is a lot of heat flowing from this ball, and the temporal dependence of this heat flow is very, very complex. This whole system is not in equilibrium. Then I cannot speak about all this extensive quantities, etc., etc. Now, is entropy is extensive or intensive? The entropy is extensive. It depends on, it grows with energy. It grows with an x. Okay. So entropy is also an extensive property. This is the function, and I would like to add here extensive function. It's part of my definition. Great. Now let's try and play a little bit with entropy. What I mean by playing, devise some sort of mathematical formulas of how entropy is behaving. So let's take a small change in entropy, differential of S. What it means, so S is a function of E and X. We can write that the change of S is basically the change of S with respect to E when keeping all my extensive variables constant multiplied by the change of internal energy E plus the change of my entropy with respect to all my different extensive variables multiplied by the change in those variables. What this simple means, right? This basically means that it is dou S dou x1 E and xs multiplied by dx1 plus ds dx2. Here I have E and x multiplied by dx2 plus etc. etc. Now those small symbols over here means that I take the derivative of s with respect to x and keeping all this other constant, all the other parameters constants. Okay, so for example, when I here take the derivative of s, this is a partial derivative of s with respect to x1, I keep E constant and also all the other extensive parameter constants. Okay. What do we know about dE? We know that the first law of thermodynamics is actually describing what dE is for any kind of a processes, right? So dE is dQ plus f dot dx. Okay. What are the Fs? Fs, those are generalized forces. They are conjugate variables with the x's. Now, when I change ds, I change it in an adiabatic fashion. I change the states or my variables in adiabatic fashion because the growth of the entropy defined in for adiabatic processes. And here, this guy here is defined for any kind of a change. Okay, I don't really care. If it's a change was performed in reversible or non-reversible fashion. Okay. So in general, I can apply this dE into my equation over here, and ds will be equals to ds dE multiply dE by x multiplied by dQ plus f dot dx plus, questions? No. Plus ds dx E multiplied by dx over here. Okay. Or we can describe it as ds equals ds dE x dQ plus ds dx E plus f multiplied by dx. Right? No, I'm sorry, there is additional term. This additional term is f, let's write it this way. This guy over here, I forgot it. ds de x f multiplied by dx. So this is a scalar, this is a vector, and this is a vector as well. Okay, so this is true always. Well, not exactly always, because I devised my ds for an adiabatic process. And now I'm asking what happens if my process, so I'm achieving my change in ds, I'm achieving ds in adiabatic fashion and in a reversible fashion. So I'm changing my parameter, I'm changing everything in such a way that the process was adiabatic, no heat was exchanged with the environment, and the process is reversible. So adiabatic means, what adiabatic means? Adiabatic. What happens when the process is adiabatic? dq is equal 0. Okay? No heat exchange. Reversible means what? What happens for reversible processes? ds equals 0. Okay? Reversible. ds equals 0. Okay. What I managed to obtain from this, basically ds equals 0, dq equals 0, so, and dx is arbitrary. Sorry. Okay. What I'm left with is all the term in front of dx has to be equal 0. Okay. So this guy is 0, this guy is 0. All of this equals 0, but dx is arbitrary. I don't know what dx is, right? So what I came to is that ds divided ds dx e equals minus ds d e x f. So f is all my different forces that I have. X is my extensive variables, E is the energy, and I obtained something that happens for reversible processes and adiabatic processes, right? This is a general relation. Now what I'm saying is, well, although I had to use adiabatic process and reversible process in order to obtain this relation, but it will always hold. Why so? S is a function of a state in X. So when I'm changing S, when I'm saying I'm changing S from SA to SB, the state A and the state B have to be equilibrium states. So when I'm writing ds dx, because S is defined as a function of state, of equilibrium state, is basically saying, well, I'm starting from state A, which is equilibrium. I'm going to state B, which is also in equilibrium. And because of this very crucial fact that S is a function of E and X, and I don't really care how I came from state A to state B, as long as it's only in equilibrium, and I can always assume that I've changed my path in a reversible way, this guy always hold. Okay? S function of a state. I can always think, because the changes that I had, that as it changes from one equilibrium state to another equilibrium state. Okay? Basically, my example with a hot ball and a swimming pool. I cannot say anything for the changes of the entropy as long as my ball over here is still not in equilibrium. But as it will eventually reach equilibrium, then the changes of the entropy are given by this equation. If I'm trying to apply it to a non-equilibrium state, it won't work. But as the minute the system have reached equilibrium, this equation holds. Why? Because I can imagine always that I reach this equilibrium state by performing some reversible and adiabatic reversible process. Does it actually teach us something, this equation over here? Well, we'll see that it actually does. And it's a very strong equation because it's only equations of states, and it relates to states and changes of the entropy during applications of external forces and during changes of my of the entropy with my extensive parameters. Now, before actually doing something else, I want to describe the state once again. So usually, when I'm describing a state or an equilibrium state, I'm using energy to describe a state, okay, as a function of state, and what defines a state for me. Extensive variables, for example, the volume, so this is energy, volume of the system, and also composition numbers. What are the composition numbers? Well, I can have molecules of type hydrogen, and can have carbon, and etc., etc., etc. So different molecules that constitute my system, N1, N2, N3, etc., and R. Composition variables. Now, when I'm defining a state, I'm using my extensive variables, X's, all of these different parameters. So the volume and the numbers of different particles. This is my X. Right? We can actually play with the volume. Maybe I can some other extensive variable, but as right now, the only thing that I care about is the volume, and also different particles that I have there inside. Okay? Different kind of molecules where the N's actually number of moles of particle type I. Great. So now I know that I have this entropy. I know how it changes. This is relation will always hold because it only depends on the state. The state variables are my energy, volume usually, the composition variables, and something is missing to define a system, right? This defined equilibrium, because we used to, and already it been at the end of my tongue for a couple of times, I'm using from time to time the word temperature. What is temperature? When using entropy and etc., etc. Because when we're talking about thermodynamics, and we're talking about materials, we're talking about their temperature. What is temperature in this language of entropy? Okay? How we actually define temperature. Usually we're doing the other way around. We have temperature and we're saying something about entropy. Now I'm saying, well, in a mathematical fashion, I have a function. It's a growing function of energy. It's defined for equilibrium. It grows or it shrinks, and it behaves as this equation holds us. What is the temperature? We know that ds dE for x held constant is greater than 0. Right? Why we didn't know it? Because it's part of the definition. It's part of our second law of thermodynamics. Entropy is a monotonic function of E. Monotonic growing function of E. Okay? So when E is growing, S is also growing. Its derivative is greater than 0. S is a scalar function, right? So we can invert the derivative, and we basically can say, well, dE with ds, when we hold x constant, so S, when x is constant, S is the whole function of E, okay? And it's greater than 0. It basically also says that E with respect to S is greater than 0 also. Okay? And my temperature will be defined as the change of the internal energy of the system with entropy, while keeping everything else constant. What is everything else? All these extensive variables that define my state, the volume, the composition numbers, are held constant. And we also know that this guy is greater than 0 because dE ds is always greater than 0. And this is temperature. Okay? This is temperature. How it's related to whatever temperature of the air that we have, we'll see later. But from our mathematical perspective of the second law, temperature is the rate of change of energy with S defined for equilibrium. Okay? It's very hard, or it's impossible to define what is the temperature for a non-equilibrium state. Temperature defined for equilibrium states, because E and S are equilibrium.
But we have learned the minus temperature. So before.
Okay. What do you mean how you have minus n? So for example in Celsius, right? The temperature is minus 10 degrees.
No, it's a error. We have learned partial E divided by partial S minus than 0. We have learned it before.
What do you mean? So what do you mean? What do you mean that the temperature can be negative or cannot be negative?
Can be negative.
Can be negative. Okay.
But it's
For
much higher than the positive temperature.
okay. Okay. So the negative from this perspective of entropy, from equilibrium, right, and from this definition, the temperature cannot be negative ever.
But by the definition of the entropy,
Mm-hmm.
and the entropy equals the E, this is the curve like this.
Okay.
This curve like this, I relate by.
Yeah. So what do you mean? What you mean is, can I have entropy that is not a monotonic function of energy?
Yeah.
Okay? So the question is, do we have systems where entropy is not a monotonic function of entropy? And all those are exotic states, and we won't treat them. There are some natural states when the entropy is a non-monotonic function of the energy. Okay? It's very hard to define any kind of equilibrium for them. Okay? And I'll try to come to this later. But because it's an exotic statement. The statement that entropy can be a non-monotonic or a function of E is a little bit problematic. Okay? Now, especially in the perspective of the 19th century physics. Think about gases, okay? And Well, we will come to this question later, especially when we'll define, now entropy is something very amorphous, okay? It is a general function of state. When we'll define entropy in a Boltzmann fashion based on microscopic states of the system, we'll come to this question later. But as for now, from the thermodynamical perspective, S is a growing function of E, and because of this, T cannot be negative, okay? Right for now. We will come to this later in the class, not today, not next week, but we'll come to this question later. Because you're right. What actually forces S to be monotonic function of E? We postulated this. We say, this is the second law of thermodynamics. Is it true or not is a different question.
But that's the definition that we made.
Yes.
If
Yes.
not,
The question is, are there some specific materials that for them this definition is not true? And the general answer is there are not such materials. Regular materials. We can invent or predict some specific materials where are somewhat exotic. And the whole discussion of equilibrium for them is exotic too.
I'm having a hard time to understand. S we cannot write still like in a function because it's a function, but you cannot.
I will come. Yes.
We just know that.
So yeah, look, the regular way is an opposite way. So regularly, I measure something, I define temperature, I define heat, I measure energy, I measure work, etc., etc. I do not measure entropy, right? Now, I'm saying, well, there is an entropy, because what they managed to understand is that when I'm taking all those quantities, extensive variables, volume, number of molecules, the heat of the energy, the temperature that they defined in a different fashion already, I can find a function, okay, which is growing with energy or behaving in a very specific way. And this function is entropy. So the usual outcome from the measurements, I know something about the entropy. Now I'm saying, well, actually, we can define entropy first and then devise everything about temperature or the behavior of the other functionals. Okay? It's easier way. It's more mathematical way to describe the situation. And it's actually saying that entropy is much more basic ingredient in the system than everything else. But you are right. The natural way of how this was discovered, nobody just thought, sat at his chair and said, well, I'll think about entropy today without doing any experiments. No. The real world works like I'm doing experiments, I have a lot of observations, and I have to make some general laws out of those observations, and what I see is there is a specific quantity, entropy, which is, we know, is related somehow to the amount of the disorder that the system has, that grows with energy, that grows with the amount of work that I put inside the energy, inside the system. What I'm saying, well, we can start the other way around. We can say, we have entropy, and everything else will follow from the definition of entropy. Okay? Now, can I exchange entropy? Can I exchange entropy and energy? Okay? So the first law says something about the behavior of the energy. Can we use the second law on our function over where it was over there in order to say something about the energy? So we know that ds dx E equals minus ds dE x f. Okay. Now ds dE x equals 1 over the temperature. Okay? Let's push it inside the system, and we will have ds dx E equals minus f divided by t. So I can now say the following. ds equals ds divided by E x dE plus ds dx E dot dx. Okay? Plug in this expression over here and obtain that ds equals 1 over t dE minus f divided by t dx. Okay? Multiply everything by E and obtain the regular expression that relates energy and entropy dE t ds plus f dot dx. So energy is a function of all my extensive variables and S. S is a function of energy and all the extensive variables in equilibrium. So for equilibrium, we can define our energy as a function of S and all the extensive variables. Great? And this expression, whoever taught you thermodynamics, you already have seen. And this also relates for equilibrium processes and changes in equilibrium, that TdS will be equals to dq, right? Because this is dE, this is the regular work that we already had, and here's standard dq. So the processes that takes, quasi-static processes, that takes us from one equilibrium to another, we can relate the change of the heat to the change of the entropy. Now, can we use this second law of thermodynamics in order to make predictions? Okay? In order to say, well, I have a system and I divided it to two systems. So I have here E1, I have another E2, and I have some specific constraint, maybe a wall between those two systems. Okay. This volume is volume 1, this is the second volume, and I have some wall moving between those two systems, and I'm asking myself, can I describe what is the equilibrium? Is there a principle to actually describe the equilibrium state of the system? Why am I interested in equilibrium? I'm interested in something stable. I'm interested if I'm leaving the system on its own, and I will look on the system after a week, and after 2 weeks and 3 weeks, and I want to describe, to see that the state of the system has not changed the function of time, saying I'm looking for the equilibrium state of the system. How can I predict what this equilibrium state will be? And this thermodynamical second law that we have learned should answer this question. This is why it's so important that we will see how we can actually use the second law of thermodynamics in order to answer the questions, how systems reach equilibrium, what systems in equilibrium, and is there a principle to describe the equilibrium of a system. So what we are going to do now is to devise a variational principle for the second law of thermodynamics. Variational principle for the second law of thermodynamics. What I mean by this is, for this specific system, the variations that I have is the movements of this wall over here, right? Imagine that I have a big volume, and my constraint is that I have a wall between those two systems. There is a gas chamber, and this wall can play around a little bit, okay? So, or I can change it on my own. And the question that I ask myself, how it was going to change, what are the variations of the positions of the walls that eventually will bring me to equilibrium. Okay. When I'm looking on this composition of two systems, I'm looking on specific constraint, the position of the wall over here. Okay? I can imagine that, or I call this wall over here an internal constraint. What I mean by internal constraint? I mean by this that when I'm changing the position of the wall over here, the total volume of the system does not change. The total energy of the system does not change also. The total size of the system does not change. So basically, internal constraint is the constraint that I can change or make, which does not changes the macroscopical properties of the system. Okay? It changes something about the subsystems, about the constituents. Okay? For example, I can make this wall such that only a specific type of particles can pass through this, and the other ones cannot. It does not change the total composition of the particles inside the system. Okay? But it changes the compositions of number of particles on the right sides and on the left side. Okay? So internal constraint is a constraint that I impose on the system, and it does not change anything globally for the whole system. It does change something or perform some variation of the local properties of the system. Okay. So imagine the following. Imagine that I have a system, and I describe the equilibrium state of the system by specifically defining what is E and what is X. Okay. So I know if I define the energy to be at specific values and all my different extensive variables to be at specific value, the system will be at some specific state defined by E and X, and this state is an equilibrium state. Let's call it A. Okay, so I'm living in a two-dimensional world, and this is my two-dimensional world. One axis is the axis of the internal energy. The other axis is the axis of my extensive parameters. And if I define 2 points on those two axes, they define completely the state of my system. Now I invent an additional state, and this additional state is where this internal constraint is actually located. Internal constraint. What I mean by this is that when I defined E and defined X, I defined it for the whole system. Okay, this is my system. It had E and it had X, for example, volume. Okay, and there were no constraints inside. No specific wall that actually divided the system into two different halves. I can think of that I imposed my wall over here. Okay? The state of the system, the total system, will change because now I have a different additional parameter that is not part of the axis. Okay? And think about it that the state of the system will get out of this two-dimensional manifold and will be somewhere over here. Okay? I can place my internal constraint over here, and the position of the system, not the position, but the state of the system will change as well. Okay? So in general, if beforehand I could describe the state of the system as some position in this two-dimensional world, now that I have constraints, I have to describe my system as living in a three-dimensional world. One axis is the axis of the energy, the other axis is the axis of the extensive variables, an additional axis is the axis of the position of the position of internal wall. So basically, I can start from here and very smoothly and diabatically change my constraint and actually start from state A and get into state B. I'm not changing energy. I'm not changing extensive variables. I'm not changing the volume of the system. I'm changing something internally, and the state of the system will change. Well, I can imagine the volume here is higher, the volume here is lower, the pressures are different, etc., etc. I can imagine a lot of situations. Now I can go from this state to this state in a quasi-static fashion. Okay? I can perform those changes, the movement of my internal constraint very slowly. Even more of that, I can, for example, drill holes in this constraint and move it also very, very slowly, and then change the number of holes and etc. The only story here is that the motion of how I'm changing the state of the system from A to B is quasi-static, means reversible, okay? Very, very slow, and everything here is in equilibrium, okay? And that the external parts, the energy and the excess, are not changed. So I've reached state B. Okay? Once I reach state B, okay, so I have my constraint over here, I have my wall, I'm doing a crazy thing. I'm saying, well, everything here are diabatic. Right? So it wasn't a diabatic before. Why? Because, well, I had to do something, so there was a flow of heat, maybe. The work had been performed. Now I'm leaving the system. I'm leaving the system. Okay. Why before there was a flow of heat? Okay, think about it in the following fashion. So dE equals dQ plus dW, right? This is the first law of thermodynamics. Now, what I've said that I've gone from point A to point B in such a way that everywhere dE was 0. Okay? So dE equals 0 because I haven't changed my internal energy. It means that there was dQ plus dW equals 0. I had to perform some work, and there was a flow of heat inside or outside from the energy. After I have done it and actually reached point B, I impose adiabatic constraints. Okay, which is great, I can do this. And the next moment, I do something even more crazy. I take this constraint and just simply delete it. Okay? So the system was in state B, right? There was some size of this constraint, and at some point in time, I just get it out, okay? While having adiabatic conditions around my system, adiabatic walls. What will happen? What will happen to the system? There is no constraint. I have a specific value of E, and I have a specific value of X. What will the system will do? Think about it.
The dW doesn't have to be 0 also?
No, I have done work.
No, but it's f dx and dx. Like
I have done something to the system, right? I have done something to the system. It's not exactly dx. Well, I have done something because I have, in order to change this, I haven't changed dx's. It's a different kind of work. I have performed the work on the system. Otherwise, how could I change anything over here? Now, the answer is, well, usually I don't really know what happened to the system, but I know where it has to come. Because if there is no constraint, the system is in a adiabatic situation, there is no constraint, I have a specific E and I have a specific X, where the system will eventually come? To an equilibrium state, right? Any time that I leave the system on its own for specific E and specific X, after a while, it will reach the equilibrium state. What is the equilibrium state where there is no constraint, as there is a given E and a given X? This is the state A. So if I'm leaving the system on its own, it will come back fast or no, I don't really care, but it will eventually come back in a adiabatic fashion to state A. Okay? Because it's an equilibrium state. So eventually, for any state B where there is an internal constraint, when I leave the system on its own, I just get out this constraint out of the system, let the system evolve, eventually it will reach point A. Because point A is an equilibrium situation of the system. So what process I've actually created? I created a state B where there is no constraint because I took it out, and I know that from this point B I will eventually reach point A in an adiabatic fashion. Okay? What the second law tells us? The second law tells us that S, E, and X, which is A, is greater. Why it's greater? Because I'm starting at B and I'm reaching A. Okay? It's greater than SB, where I have energy is the same energy, X's are the same X's, but how I define the state, I need to define an equilibrium state. An equilibrium state, B, okay? What defines equilibrium? E and X is not enough to define equilibrium in state B. I need what else? I need the constraint, right? Constraint. Internal constraint. So what I have done, or what I have obtained, I managed to devise the following rule. And the rule is, if I have a system, and it's in an equilibrium, application of any internal constraint, right? Because it will always hold, application of any internal constraint in such a fashion that it does not change the internal energy, total internal energy, and the extensive variables. If I introduce any constraint to the system, it actually lowers the entropy. Okay? And it's different from what you have said. You have said, well, entropy lowers the energy. Entropy lowers the applications of internal constraint. So if I have an entropy, I don't know how to that's defined for a general system. It defined in equilibrium, and I'm saying I'm going to change my system in what fashion? I'm going to change my system such that I will create here a specific constraint. I'm doing something to the system. I'm not changing the energy. I'm not changing the volume of the system. I'm not changing the total composition. But I even knowing something about the system, I divided it in such a way that, for example, particles, hydrogens cannot come from this part to this part. I know the moment I have done this, the entropy of this system in equilibrium has to be lower than the entropy of the system without constraints. Okay? How it helps us? Okay? This is called maximization property of entropy. For equilibrium, the entropy is of a system is maximal when there are no internal constraints introduced into the system. Anytime that introduce constraints, the entropy becomes smaller. Because it helps us. The answer is yes. Because remember, our initial question was, what is equilibrium? Okay? How I define equilibrium. Some operational way to find equilibrium, right? If I have two systems, okay, E1 and E2, and I ask myself, in equilibrium, and they are divided, there is some wall defining, and I ask myself, what are E1 and E2 in equilibrium? Okay. I don't really know what E1 and E2. I just know that the system has adiabatic walls, for example, and the total energy is conserved. Okay. I have two subsystems. The system is isolated. The total energy is conserved. Okay? And I'm asking, what are the values of E1 and E2 such that they define the equilibrium of the system? I can think, well, the entropy energy here is 0, and the total, all the energy is in this part. Good or bad? Defines the equilibrium state or not? The maximal principle, maximization principle of entropy gives me the right answer. Because it says, in equilibrium, the entropy is maximal. Okay? Because if I'm going outside of equilibrium, I will start to change a little bit my constraint over here. I'm starting to change the composition, or I'm starting to change the position of this wall. What will happen to the entropy? The total energy won't change. There is no adiabatic change with the environment. But the entropy will go lower for any state that it's outside of the equilibrium. Okay. So in equilibrium, S of E and X such that this constraint E1 plus E2 equals E is maximal. Right? So this is a strong statement. The statement is that there is a function, and this function has to attain its maximum at equilibrium states as a function of what? As a function of local changes to internal properties of the system. When I'm doing something internally, okay, transferring some of the particles from here to there, okay, it's for sure going to lower the energy of this, not the energy, the entropy of the system. So the maximal of the entropy happens only in equilibrium. It will go down if I'm starting to change the constraints, right, or the internal compositions. But exactly at equilibrium, it will be maximal. There's actually a very cool statement, especially if we take into account that we had very, very little at the beginning. We just said, well, there is a growth, a function that grows with energy, and that's it. And then we obtained, well, actually, it's not just growth, It's also attains a maximal as a function of the internal changes. Very nice. Now, we have seen that there is a relation between energy and entropy. And we know that entropy in equilibrium also defines energy in equilibrium. So if there is a maximal principle for entropy, can we think about maybe somewhat related principle for energy? Okay. And what we are going to derive right now, it's a minimization principle for energy. Any questions you can ask. Don't worry, I won't bite. So let's assume that we have a system, it's in equilibrium. Okay? It's in equilibrium. And there is part 1, it has energy 1, and it has part 2, and it has energy 2. And we know that E1 plus E2 is the total energy of the system. And I'm asking you, what will happen if we apply a variation, okay, to the system such that I will change a little bit, the energy of E1 will change and the energy of E2 will change, okay, but the total energy won't change. Okay? So I'm changing the system internally. I'm applying an internal constraint. I'm changing this wall a little bit. I'm building a small holes in the system. But I'm doing something, right? I'm doing something to the system. And after I have done this something, E1 had been lowered by delta E, and E2 gained some delta E. Okay? Small change. The extensive variables, I haven't changed anything. The total energy is still the same. Now, the maximization principle of the entropy tells us what? The entropy in this state, S minus delta E x1 plus S E2 plus delta E x2. Okay, this is entropy of this part. This is the entropy of the second part. Okay, after I have applied my constraint. Okay, and this is smaller than what? The energy and the entropy of the total system without any constraints. E1 plus E2 x1 plus x2. Okay. So this is the principle of maximization of energy, of an entropy. Okay? I have a system, it's in equilibrium, there is a specific entropy that associated with the state, and I know if I will change the state a little bit by application of local internal constraints, okay, the entropy will be smaller. Why the total entropy of these two subsystems is just a sum? The entropy is an extensive quantity. And since it's an extensive quantity, a sum of two extensive quantities is the total entropy of everything. Okay? It's just by definition. How it's related to energy. Okay? I haven't changed the total energy over here. Right? Well, here is a small trick. We remember that the entropy is monotonically growing with energy. So there should be E some value of the energy that is actually smaller than the total energy of the system, right? I can imagine that this is a value 5, and I can imagine that there exists some value 4, okay, which is smaller than 5. It's just scalar quantities, such that the entropy of this same system, not divide, without any local constraints, but I just lowered the total energy, I know that the entropy of this system, SE, x1 plus x2. So the only thing that I have done, I've lowered the total energy of the system. And I just found some general quantity, general value of the energy. I know that this value holds, right? S E1 plus E2 x1 plus x2. Okay? I can find some obscure value of E that is smaller than E1 plus E2, and according to the definition of entropy, also the entropy should be smaller. Great. But this guy is already bigger than this sum over here. Okay. So I can generally find such E that S E1 minus delta E x1 plus S of E2 plus delta E x2 equals to S of E x1 plus x2. What I have done here, I just said, well, the entropy lowers if I apply an external constraint, the entropy of the system becomes smaller. But what I want to do is actually apply the constraint, okay? Actually take some of the energy and from E1 and transfer it to E2, but keep the entropy constant, okay? So the total entropy have not changed, right? The total entropy of the system when I apply the constraint is exactly as before. S, the entropy of the system is before the constraint and after the constraint is the same. But what have actually happened? E have changed now. The total energy have changed. And what happened to the total energy? It became smaller. Right? It became smaller. So if the process that I want to make is I am applying an internal constraint, but in the same time keeping the total entropy of the system constant, the energy have to go down. Okay? The energy have to go down. Oh, I'm sorry. Not the energy. When I'm the other way around. So when I'm starting from a system and I have some specific entropy and I have a specific energy, the entropy is given by this quantity. I'm applying an internal constraint such that the total energy is not changing. So this is before and this is after. So before I apply the constraint and after I apply the constraint. The entropy is the same, okay? But the total energy is different because what is the energy before? It's E. What is the energy after application of the constraint? It's E1 minus delta plus E2 plus delta. What is E1 minus delta plus E2 plus delta? So before application of constraint, I had energy E. after application of constraint, I have E1 minus delta plus E2 plus delta equals E1 plus E2. The only thing the thing that was actually kept constant is the entropy. I apply the constraint, I kept the entropy constant, and I get a change of the energy from E to E1 plus E2. And I know that E is smaller than E1 plus E2. Because this is how I started over here. So application of a constraint for energies while keeping the entropy constant, okay, increases the energy. Application of constraints, this is called a minimization principle of the energy. Okay. Minimization principle of the energy. So, application of constraints while keeping entropy constant increases the internal energy. For entropy is the other way around. For entropy, application of internal constraint, internal constraints, while keeping energy constant, decreases the entropy. Decreases the entropy. Okay. So at one time I keep entropy constant, at the other or the energy constant. For entropy, it decreases. For energy, it increases. Now you maybe remember that you learned that when a system is left alone, after a while it will get to the minimal energy. This is exactly this claim over here. Entropy is related to the number of states that the system has. So while keeping the number of states constant, the equilibrium state will be the state where the energy is at minimum. The other way around for entropy. Entropy, while keeping energy constant, is the situation where the number of states is maximal. And this will appear when we will relate entropy and the number of states. Will come to microscopic description and Boltzmann definition of entropy later. Okay. But as for now, we see that there are two strong arguments about minimization and maximization of entropies and energies for equilibrium. Okay. I don't really have time to describe you an example of what will happen, what happens to the system if I apply those principles. But what I can show you, and I will show it to you next week, is that the regular description of the second law. What was the regular description of the second law? What happens, for example, if two systems are kept together in a adiabatic fashion and have E1, X1, and T1, and I have E2, X2, and T2, okay, two systems, kept in equilibrium, there is a diabatic walls around them, and T1, and what is the connection between T1 and T2? Okay. Moreover, if I take two systems with different T1 and T2s and bring them together, what will happen then? Okay. So basically the regular questions of the heat flows from a hotter system to a colder system, and in equilibrium the temperatures are exactly the same, which is the usual statements of the second law of thermodynamics, will appear as an outcome of those principles of definition of entropy, or connection between entropy and energy, and the maximizations, or what is called variational principles for the entropy and the energy. But all of this will come next week. Thank you.